Okay, I believe everything should be in order. I will chuck in the exam 2019 Tech 3. We got up till just before question 3 last time, and so we shall start at question 3. I'll put that in the chat if you grab your own copy should you wish. Let's have a look. The only possible outcomes when a coin is tossed are going to be head or tail. When an unbiased coin is tossed, they have equal probabilities. There's 3 coins, 2 are unbiased, so normal, and 1 is actually biased, so they'll have different probabilities of head tail. The biased one has a probability of 1/3 for tossing a head. We're selecting one of those coins at random and tosses it. Find the probability of tossing a head. So you've got to sort of figure out how to handle the situation where you've got both biased and unbiased coins in the bundle, so to speak. I'm seeing your thing light up, but I
Is
can't
it
actually.
is it 4 on 9?
409, yeah, 409 is correct there. It was just lagging for a second. Yeah, 409. So you probably said, yep, I got a 2/3 chance of getting the 50/50 one, and I got a 1/3 chance of getting the 1/3 chance thing. And so yeah, adding those up together, 409. Perfect. Find the probability that she selected an unbiased coin, given that she tossed a head. This one's probably easier than you imagine it to be. So the keyword given that implies conditional. So you've now got to expand that out to your conditional probability formula. So basically you want to find the intersection of an unbiased coin and tossing a head, which we may or may not have already done, divided by the probability of the conditional, which in this case is a head, which we also may or may not have the probability of. This one is a 1 marker because you've actually already solved all the probabilities required to calculate it. We're just arranging them up.
Chris, is it 2 on 3?
2 on 3. 2 on 3 is a bit off, unfortunately. How'd you come to that one?
So intersection. I'm not really sure exactly sure how to figure out the intersection. I thought it was 4 on 9.
That's the previous answer. 409 is the probability of head, actually.
Yeah.
So that was the answer to this one. Find the probability of head. So 409 is your denominator in this case. Intersection just means both things are happening at the same time. So
So
probability of
is that 1 on 3, the intersection?
1 on 3. Uh, no, because you've got 1 on 3 by 1 on 3. You've got the probability of it being unbiased and then the fact that it's got to be a head. So a head is 1 on 3 on the unbiased, but you've also got a 1 on 3 chance of hitting the hitting that probability. Um, which, yeah, sorry, that does actually. Yeah, what am I saying? I'm looking at the other one. It does end up being 1 on 3. Yeah, you're right, because it was 2/3 for unbiased. My apologies. 2/3 for unbiased, and then multiply by the probability of a half. That gets you to your 1 on 3. And so yeah, that's all that's really going on there. You take it's this one here. So biased intersection head. Wait, what am I looking at? What even was it? Unbiased coin. Yeah, unbiased. This one. That's the one that you want. And then dividing by probability of head, which is the 409. This divided by that should get you the 3 on 4. Make enough sense? Next up, solve a set of cosines. This is a very standard question. Done a lot of these.
Chris, if we brought the negative cos x on 2 to the other side,
Mhm.
would that make it like 2 cos x on 2 or not?
Sure would. Yeah.
Okay.
Cos of something plus cos of something is 2 lots of that cos of something.
Are the solutions negative 5 pi and 3, negative pi and 3, pi and 3, and 5 pi and 3?
Maybe to
Oh,
the
actually, hold on,
initial.
hold on.
Yeah,
Okay, never mind.
that's fine.
Is it plus minus 2 pi and 3?
Plus minus 2 pi on 3. Yeah, that's
Yeah, I
right.
forgot to eliminate solutions.
Oh, sure. Yeah, okay. Yeah, just double checking the domain. That's pretty much it, I suppose. Yeah, so to maybe show in a bit more detail what's going on there. Yes, combining those cosines is a great idea to start with. Cosine equals half occurs at plus minus pi on 3 plus minus 5 pi on 3. I basically just started with that, multiplied by 2, and just figured that would be good enough. If I needed more solutions, I would find more. Because you can do the whole thing of figuring out your effective domain ahead of time, but at this stage we're pretty much all capable of just chucking out the first two plus minus solutions and then going from there. Cool. Part B, you'll notice is a quite similar circular function over the same domain. G is going to be written in terms of f, 1 minus f. Sketch the graph of G. Yeah, that's pretty much it. It'll be a bit easier if you have your own physical copy that you can basically make use of the symmetry of the curve you already have. But yeah.
Is the reflection on the x-axis is shifted up one?
Mm-hmm. Yeah.
I'll see the coordinates real quick.
Oh, sure.
And the coordinates are just plus minus 2 pi and 3.
Yeah, there you go. There's a certain similarity in there. Yeah, so it'll end up looking like that. Yeah, that's pretty much it. Now, as far as what you have to have labeled, you would also want to have your endpoints labeled as well. Yeah, intersection points and endpoints was all that was required for that one. That and the curve, obviously. But yeah, as for how you would get those intersection points, it would have just been cos x on 2 equals that, and you'll realize it's literally just that equation for a over again. Cool. Smashed out circular functions. On to question 5. Really basic question. I think we can probably just skip AI. There's not much to talk about there at all. Might as well do double I though, just double checking you guys can still sketch the truncus. That, and you'll probably want to have the picture of it anyway to solve part B.
Is it just like a normal like we don't really need to factor the dilation because there's no other graph here, but
Yeah.
um I think horizontal asymptote at y is equal to 1,
Mm-hmm.
vertical asymptote at x is equal to 1, and you just draw the truncus across those asymptotes.
Yeah, precisely. Pointing upwards specifically is what you're looking for, and you want to give a y-axis intercept for that. But otherwise, yeah, that's all. Nice. Wait, did they? Yeah, okay. Yeah, you actually already got a copy of that in the solutions. So if you want to refer to that when it comes to calculating your area for the part B, you've got that there as well. Area bound by F, the x-axis, and these two x equals lines. This one's pretty much free as well, especially once you refer to the picture. It's a fairly typical application of using your integrals, right? You want to find area under curve bound by some number of lines or curves, just doing definite integrals. To practice a bit of anti-diff, and then from there it's just a bit of algebra basically. There's a formula sheet in the in I think both the documents, but definitely the first one. If you want to refer to how you could anti-diff the truncus, because I know that can be a bit of a pain. If anyone's still unsure, we're basically finding this section of area in here, because it was bound by the x equals -1, the x equals 0, and the blue f of x line, and the x-axis. And so to do that, you would just integrate from -1 to 0 of your f of x. That requires you to anti-diff and then do capital F of top.
Chris, is it 2 units squared?
Yeah, that'll do it. Nice. Yeah, so that thing in the brackets there would have been the anti-diff of your function, and then you're doing capital F of top, so 0, minus capital F of bottom, so capital F of -1. All that being simplified. You're basically dealing with linear there at that point. And so yeah, that's going to give you 2. Just based on the exam report, I guess I don't really care too much if you give units squared or not. They didn't mention it, I guess, at the very least. But yeah, that's about it. More probability. Question 6. Randomly selects 41 pegs that are produced on one day, 8 are faulty. What is the proportion of faulty pegs in the sample? Some keywords there can really help you hone in on exactly what kind of probability we're dealing with. And that will vastly restrict the amount of things you can do here, which is a good thing. You want to have a very clear way forward. Okay. First hint is that this is the sampling and estimation chapter. So they're using the keyword sample, they're talking about proportions. So it basically guarantees what they're talking about is sample proportions. Proportion of faulty pegs in the sample just means what percentage of them are faulty out of total. That's what it's really talking about. Now, obviously, you don't have to give it as a percentage, you can give it as a fraction. by that I mean you don't have to use a percent symbol. So effectively another way of reading this question would be to say, what is what are the percentage of faulty pegs in the sample? Proportion, percentage, meaning the same thing, effectively. Oh, no. No one's taken a stab at it. That's either mildly concerning or maybe someone's just AFK. One of the two. Okay. We might need to brush up a bit on the sampling. Yeah, 8 on 41. That's what we're looking for there. Yeah, it meant to be a fairly straightforward question there. You've got 8 that are faulty out of a total of 41. The proportion is therefore 8 out of 41. The percent likelihood of selecting your that's basically your p hat, right? P hat x on n, x being not a trick question. Um, that's fair though. It's fair to be a little bit suspicious as to what's going on there. The trick questions, I don't. Yeah, this is anecdotal, so don't quote me on this. I'm pretty sure they save a lot of the trick stuff that's a bit bullshit in the tech actives because they feel like you've got all the resources you could possibly have at that point. I feel like the tech frees are fairly streamlined, so you can probably be a little bit less suspicious in tech free, but that's fair. Cool. Pegs are packed each day in boxes. Each box holds 12 pegs. P hat is, as before, proportion of faulty pegs. The actual proportion is going to be 1 out of 6. Find probability P hat is less than 1 on 6. So P hat is sample proportion. Actual proportion is a different thing. Or at least it means a different thing. Slightly. Remember, sampling and estimation differentiates between two types of definitions, one being the local sample proportion and one being the global population proportion. This one's just saying a fine probability of p hat being less than 1 over 6. Express your answer in whatever. More importantly is getting our head around how do we solve probabilities in sampling and estimation. I'll leave that be for now, so you guys can have a think. The hint will be you typically don't solve things purely with the proportion numbers in them. You do some sort of conversion to make them a bit more useful, or at least closer to something you're already a lot more confident with calculating. You typically won't use p hat numbers, you'll convert them in some way. the trick is to convert it to discrete. So p hat being 1 on 6, you can now treat that and try to rearrange it in terms of x instead. So if p hat is the same thing as x on n, and we can determine pretty easily what n is going to be, since each box holds 12 pegs, what we're going to have is a way to convert that 1 on 6 into an equivalent x value. So we have p hat being x on n is equal to 1 on 6. We're just looking at the breakpoint specifically. N is 12. And then from here, well, it should be fairly obvious that you're going to have x equals 2, which you can obviously do some algebra math to solve for. But yeah, you're going to have x equals 2. And so effectively, you're going to now rewrite your probability equation as saying x less than 2. Remember, you've got to maintain the same inequalities there. We're just converting that 1 on 6, a proportion, into x equals 2, a discrete value. Because now we can treat it like discrete. I'll leave that there for now. Probably the final thing you'd have to consider here is to treat it specifically as binomial, the subset of discrete. And so if we think about how we solve binomial probability, we, I guess firstly, why is it binomial? Well, you've either got faulty or not. That's pretty much what it boils down to. There's also implied independence in there because you have a global population proportion of something occurring. You know, if the probability of any given peg being faulty is, what was it, 1 on 6? Yeah. Your p-value being 1 on 6, that's the same as the binomial p-value. And so, if we think about how we calculate binomial probabilities, it is Bernoulli sequence. And so we're essentially just doing a sequence of Bernoulli sequences here for all x values less than 2. So you're talking probability x equals 1 and probability x equals 0. Let's not forget that one. Are people getting close to an answer, or shall I just reveal some sample working out? Okay. Here's what I have in a Word doc that I've had for God knows how long. So that's our conversion into x less than 2. And then from there, that's just your x equals 0 plus x equals 1. You expand that out with your full Bernoulli sequence. So for x equals 0, you want 0 successes. So 1 out of 6 being because you're talking about the number of faulty here. So when you have 0 successes, it's in this case talking about 0 faulty. 12 being the sample size, n, same n in binomial. And so yeah, create your 2 separate Bernoulli sequences there. This thing just completely disappears, leaving you with just your 5 on 6 to the power of 12. This one doesn't fully disappear. You're still going to have your 1 out of 6 and your simplified version of this, which just comes down to 12. And what saves us a little bit is the fact that we're supposed to give our answer in a particular form. Like, trying to calculate all this would be a pain in the ass, the actual numbers themselves. And so, lucky for us, they said, hey, give me a coefficient, give me a base, give me a power. And so we've done exactly that. The key thing to identify here was noticing the common power, the common base of 5 over 6. You can take out as much of that as possible, simplify the inside there, and, well, yeah, that's all that's left. Any questions about that one? Cool. Let's move on. Do it? Yes, I do. Question 7. Graph of the relation. We got a triangle inscribed into it. We've done actually, I feel like we've done surprisingly few of these. It's a very common question from what I've come across, but I feel like in these classes we've done not that many of these. Maybe they show up mostly in multis and stuff. Surely not in multis. Anyway, first question is not so bad. Find an expression for the length PB. So just what's this vertical distance here? That should be fairly chill. But the problem is you've got to get it purely in terms of x. That's the only little trick to it, I suppose you could call it. That was enough to trick approximately 40% of students. So I guess so. So the obvious initial answer for the length of PB would just be y, right? Like, you got y equals 0 all the way up to y equals y. That's an obvious starting point there, the length of that PB, purely vertical. But that's a y, not an x.
Okay, so are we able to state root 1 minus x squared?
We sure can, yeah. So the point P exists on that relation. And so for that reason, you can replace that y with the square root because, well, that's where it's located. And so, yeah, that's that. That's the trick for all these, by the way. Whenever you have a shape that's inscribed into a different kind of function, you can always make use of that property, which is you can replace every y with what the actual equation is. And that's used in, I think, literally all the solutions to those kinds of questions. It's a key step in them all. Which will now exploit in part B, finding the maximum area. Keyword maximum. That gives us a few ideas as to how we might go about it. Area, well, that's another thing we should be fairly common or fairly familiar with. If for whatever reason you forget how to create your area equation, I believe it's in the formula sheet. It's more of a time-consuming one, especially this one in particular. You've got a lot of little terms floating around. Though once you do get over that hump of messing about with a bunch of terms, you realize that a lot of them disappear pretty quickly. So probably the first thing you'd be interested in doing when it comes to maximizing area is to first have an equation that describes area. You can't maximize something until you have an equation that describes that thing. Area of triangle, half base times height. So you want to figure out how do I get my base and how do I get my height. One of those is already solved for us. The other is pretty quick to get.
Chris, is it going to be x plus 1 times root 1 minus x squared all over 2? And then we solve for the maximum?
Sorry, say that. Is that your area equation?
Yeah,
Say that one again.
x plus 1 times root 1 minus x squared all over 2.
All over 2. Yeah, okay, that was good. I thought you might have had one in the bottom by accident. No, that was good. Yeah, so x plus 1 being the length, right? You've got x as one endpoint, -1 as the other. So you've got a total distance of x plus 1. And then the height, of course, we had that from before. Yeah, that's good. From here, we're looking to maximize a thing. So this should start bringing about things like trying to find derivative. Derivative is often used when finding maximums. You will need it, even though it is a bit of a pain to grab it, because you're basically looking at a product rule there. X plus 1 times the square root of 1 minus x squared. This is where the terms get a bit nasty to play with. Depending on how far you simplified your derivative, it should look something like what I've got written down. And the reason why I phrase it like that is because you don't necessarily fully need a simplified derivative. You just need it in a spot where it's good enough to use for the following equation that you're going to create with it. Once you have derivative, the whole point there is that maximums or minimums tend to occur at turning points. Yeah, correct. Make it equal to 0. It's exactly what you want to do. So yeah, we're going to take that derivative in whatever state you had it in, make it equal to 0. This would be the easiest state to have it in, because when you have a fraction like this, you can just multiply both sides by the fraction. You don't have to worry about any potential of this being 0, because, well, if it was 0, then you'd have an issue, which is a divide by 0 error. So you can pretty safely, oh, what am I saying anyway? You can always multiply by a number like this. It's only whenever you divide both sides by variables you run into problems, or could run into problems. So it very quickly simplifies to just negative 2x squared minus x plus 1 equals 0, and I would personally go a step further and flip those to be positive by just multiplying both sides by a negative. That makes it a little bit easier to work with. Whether you do quadratic formula, whether you do factorizing, both can work, although factorizing can be, actually it's not so bad. That whole grouping method approach of factorizing these kinds of things isn't actually all that awful. Doing your AC and then adding up to give B, that actually isn't all that bad. Might honestly be worth doing that over a quadratic formula, depending on how confident you are with that sort of thing.
Chris, do you get x equal to half and x equal to -1, and then
Yep.
we sub back in to the original equation to see which one gives us the higher value?
I reckon you could figure it out without subbing in. Obviously, you'll need to sub at least one of them in because you need to get the maximum. But
No, I think I can see which one it's going to be.
yeah. Now, there's a couple of ways you could have came to that conclusion. What was the thing that gave it away?
If you sub in -1 to the equation, you're going to get like a 0. And
Okay.
then,
So you're looking at the A of x?
yeah.
Yeah, -1 directly in there, you can see pretty quickly that's going to go to 0. Cool. The other thing you could have probably looked at is A dash. You sub in negative and you get undefined there, because you've now got to divide by 0. The other thing you could have done also would be look at the picture. So remember that x is just the spot at which you're going to create how far across you want to create your triangle. And so if you put x at -1, you've now got a dot, not a triangle. And so yeah, there's a bunch of ways you could have concluded which one to sub into. I guess there wasn't too much of an opportunity cost there. If you did sub in -1 first, you pretty reasonably figure out it's going to 0 immediately. So yeah, all that's left is subbing in that x equals half, and you're going to get your value that you're looking for, which is just pure algebra.
Is it root 27 on 8 or 3 root 3 on 8?
Yeah, that one's better. 3 root 3 on 8. definitely want to give it in the fully simplified version. Yeah, I guess maybe just for the recording, I'll show some solutions I had cooked up from a year ago. What did I do? So this is all the diff stuff. You create your equation, diff product rule. There's your a dash, make it equal 0. This one's a quadratic formula approach. And then here's what it looks like when you sum in your x equals half. Someone can pause the video if they care to look at the solution there. Okay. Question 8. Find the rule of f. This one can be really, really painful or really, really easy. In fact, it might as well... have we got enough points? 1, 2, 3, 4... Oh yeah, 5, because the origin. You could do a 5-way simultaneous. Wouldn't recommend it. You're in a tech free.
Can we give it in factorized form?
Absolutely, you should. Yeah.
So would that be like a negative x squared and then times x minus 1 on root 2 and then times x plus 1 on root 2?
Kind of. Yeah, a lot of that's good. Some things are missing there a little bit, and it's not fully factorized in a sense that the two linear terms, they can combine into one factor. There's one other thing missing, which is the dilation factor at the front. You always have this implied a at the front of all of them that you have to make sure you get the a correct. It's definitely a negative number, but not -1.
Right.
Wait, sorry, what did you say your linears were?
X plus 1 on root 2 and x minus 1 on root 2.
Nah, so for the linears you want them to be
Oh, wait, wait,
x-intercepts.
my.
Yeah,
X minus 1 and x plus 1.
yeah, that's better. I was going to say something about that doesn't, yeah. Yeah, all good.
So can the linear just be simplified to like x minus 1 squared?
X minus 1. No, because you've got x minus 1, x plus 1. They don't condense like that. You just want to expand it out. So x squared minus 1 is what you're looking for there. Unless I misheard what you said. Like x minus 1 squared, maybe you said x plus 1 squared, one of the two. It's a bit different to your x minus 1, x plus 1. Not too sure when about you cut out, if it was because I don't know how long it takes Zoom to update. Did you catch what I was saying before?
No, I think I missed it.
I think you missed it. Yeah. So I think I heard you say x minus 1 squared was the condensed factorized.
Yeah, it's x squared minus 1,
Yeah,
isn't it?
that's better. Yeah, x squared minus 1. Yep, so that's that. I believe all that's left is the a term, because I think where we're currently at was we had y equals negative something like that, negative a x squared because the turning point at the origin, and then we had the x squared minus 1, that factor that we've just discussed then. There's one key thing we always do when it comes to solving for a in these kinds of questions.
We sub in one of the points.
Solving one of the points is correct, yeah. Now, bit of a challenge. Some of the points, most of the points, don't actually help. Anything that would cause the entire function to go to 0 would also delete the a. So unfortunately, you got to pick one of the 1 on square root 2 points. Since that's how one that will actually maintain the a. Yeah. In fact, yeah, we're getting kind of short on time. Maybe what I'll do is I'll just share what it's going to come out to. Because that's just algebra at that point. So we end up with something like this. You sub in the point, simplify, 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 simplify. You end up with -4 being your a value. And so in total, you're going to have the, well, that f of x. -4, x squared take 1, x squared at the back. Usually you have x squared at the front, but apparently I was just feeling a bit special that day. And apparently I also felt compelled to show, God, how much of this did I do? No way. I'm insane. Did a full simultaneous just to show you not to do it. Fair enough. Yeah, cool. Yeah, let's read back. H of x. So now we've got an unknown domain, D. We've got log of g of x, where g is the same as f. Thanks. G is the same as f. And then you've got a different log altogether. And D is a domain, I guess, of the combination of these things. Bit going on. So think about where logs are naturally defined, and then think about the fact that you've got multiple logs to keep track of.
Okay, so this is gonna be like a polynomial division because we can use like the log laws.
So for these specifically, using log laws actually hides things. Because when you have a set of logs, each of them comes with their own implied domain. And if your poly division simplifies things, removes factors, like how we see in solving limits, where you try to cancel out the denominator, you start hiding potential issues in there with domain restrictions. Like, I forget the exact sort of thing, but it was like some sort of quadratic on top of some linear, and you had x cannot equal 2 because you had a divide by 0 issue. But if you had factorized the top and cancelled that out, you would end up with like x plus whatever, and there would be no evidence of like why can't we shove in 2 into this. So yes, it's algebraically okay to get a rule out of it, but when you're considering domain, you do have to look at each of these individually. And so you would look at maybe the first log, or I guess it depends on which one you feel is easiest. So g of x is the same as f, so that's technically the easiest one because you can actually just look at the picture and figure out, based on that, what would be valid for the first log. Second log, you'd have to draw your own little picture again, and then basically mash them together, see where they have common domain.
Chris, could you just go over like how you can determine the domain of like when you put a function in a log? Because I'm not really sure
Yeah,
how to.
okay. Basically, for any log to be valid, the brackets inside the log have to be greater than 0. They have to be positive. Right, we can never have a 0 in a log, and we can never have a negative in a log. And so basically, we're going to have to figure out two things. One is, where is g of x positive? And then that will be all the valid things for the first one. The other is, where is the x cubed plus x squared positive? So both of these being just greater than 0. We have to figure out both of those circumstances. This one probably feels like the toughest to look at or deal with because you've got some really nasty polynomial. But because you actually have the graph, you can actually just see, hey, where is it above 0? And that's going to be for all anything in between -1 and 1, exclusive of the -1, the 0, and the 1, because you don't want it to ever equal 0. So this one in particular is going to have, how would I even, I guess you could say something like this. X is an element of real excluding, and then you use these, -1, 0, 1. No, that doesn't work at all. That's the, yeah, okay, let's fix that. That's what I get for trying to be fancy. -1 to 0, union 0 to 1.
Does it not work when we do -1 to 1 excluding 0?
Yeah, that should be good. X is an element of -1 to 1,
And the like
exclude
angle line, yeah.
0. Yeah, that should be good. But saying that non-zero, yeah, I think that should be good. But yeah, that's the first one there, G. Second one, or last one here, just because we're low on time, I'll quickly blitz through this one. So you'd, again, try to graph it. Take your common factor x squared at the front, x plus 1, positive cubic, so it starts bottom left, ends top right. It's got to turn at the x equals 0 because it's a squared bit, and oops, because it's plus 1, it's got to cut at -1. So it's got to cut at -1, turn at 0, and then from here, once again, you're going to have basically all of this is good, excluding that, but we're already kind of doing that. So, so is that just still the same thing then? Exclude negative, oh, this one's got to, oh, it already does exclude -1. Exclude -1, exclude 0. And then this has just got a cut off earlier. So yeah, looks like it's just that. Let me quickly double check to make sure. Yeah. In fact, in my notes, I also had -1 to 1 exclude 0. So In some ways, I might have been better. In some ways, I'm worse than I was before. What the exam report have? Yeah, okay. Cool. 9%. There you go. See, bit of a pain. But these aren't hard questions once you understand what it's actually asking you to do. Probably the main challenge there was seeing g of x in there and thinking, oh shit, what do I do about that? Which is kind of why I teach the graphing version of solving inequalities. One, because doing sign analysis on 7 separate terms is a pain. But two, because, well, the graphs are usually quite easy to draw, and you may even just have them to work with. Yeah, I'm here for any questions if you want to quickly clarify things. Otherwise, I'll stop taking your time.
Thanks.
No worries.